Good afternoon or good evening. Oh, I didn't see you come in. Good. Terrific. It's a pleasure to welcome you all this evening. I'm Danielle Allen, the director of the Edmund J. Safra Center for Ethics, and we are pleased to be a co-sponsor along with the Carr Center and Director Matthias Rissa of tonight's lecture, a lecture that is both a public lecture for the Safra Center and a keynote for the opening of a Carr Center conference that runs all day tomorrow on the 70th anniversary of the UN's Universal Declaration of Rights, of Human Rights. And the conference is addressing the question of the relationship between artificial intelligence and the human rights legacy. So it's terrific to be able to start here thinking about algorithmic fairness. This is an important moment, obviously, for thinking about questions of ethics. The world has woken up to challenges with ethics and technology in a way that those of us who work always in this domain sort of sometimes wonder why it takes people the time it does to see the salient normative or ethical dimensions of a question. Nonetheless, it's fair to say that the world has generally woken up. And there are some specific reasons for this that it's worth identifying out loud. At the heart of lots of people's worries about our current state of affairs is the question of technology and the way it's changing human life. The changes are visible to all of us. Technology is accelerating in the space of law, the use of algorithmically based decision-making, that's being integrated into judicial structures. In policy, there are the questions of how to govern technology regimes. These are pressing questions and hard ones. Business is full of new business models, for example, Amazon, that are putting pressure on old models of anti-competition policy. So there's a wholesale transformation of the world of work as well, of course, thanks to technology. In medicine, developments from polygenic genetic research, synthetic biology, and stem cell research are transforming the very definition of the human, our expectations for human life, our clinical possibilities, and our intuitions about fairness and human flourishing. In politics, transformations of communications ecologies and surveillance techniques have radically altered balances of power within and between countries. This rapid technological change has brought questions of ethics to the fore in all of these domains of inquiry. That is, normative questions about what we should do individually and collectively. Those normative questions have, of course, always been with us, and reasonably stable answers to them, though, have been disrupted by the rapidity of this social change. So in other words, although these questions aren't new, there are many places where we had stable understandings of how to answer specific normative questions thanks to the stability of our institutional structures. And as our institutional structures are bending and changing and adjusting under pressures from technology, the normative questions about justice, fairness, flourishing, and efficiency are returning to the surface for fresh consideration. So it's a moment of ferment. And in this moment of ferment, there's a great deal of innovation emerging. Just to give you a couple of examples from the pedagogic realm. It's terrific that in the last few years, the philosophy department, for instance, has worked with computer science to invent a new approach that they call the embedded ethics approach to pedagogy. And this is a model for thinking of the relationship between philosophy and specific domains of positive or technical expertise. This pedagogic model builds on case studies that emerge from a specific field of inquiry and scaffold the ability of students to identify and respond to the ethical issues at stake in the case. This embedded ethics model that philosophy and computer science have developed aligns with work the Safra Center has been doing over the last 3 years or so to build pedagogic models that rest on a three-legged stool, so to speak, uniting normative inquiry, what we should do, positive inquiry, the descriptive work of the social sciences, and policy, clinical, and other kinds of applied practical work. As with embedded ethics, the Safra Center model does not seek to cultivate interdisciplinary practitioners, right? Not trying to build people who in themselves embody the blend of disciplines. Instead, the model rests on multidisciplinary partnerships. That sounds like an academic technicality, the difference between interdisciplinarity and multidisciplinarity, but it's actually important because it's about the power of partnership to bring the strengths and tools of different disciplines together to answer questions that are harder than any one discipline can answer by itself. It's that kind of partnership that motivates tonight's lecture and the great pleasure and privilege and honor I experience in being able to host Cynthia Dwork this evening. So you all know Cynthia. She is an extraordinary computer scientist, the Gordon McKay Professor of Computer Science at the John A. Paulson School of Engineering and Applied Sciences here at Harvard. She's also the Radcliffe Alumni Professor at the Radcliffe Institute for Advanced Study and an affiliated faculty member in the Harvard Law School. She's renowned for placing privacy-preserving data analysis on a mathematically rigorous foundation. A cornerstone of this work was the invention of differential privacy, a strong privacy guarantee that Cynthia tells me with excitement will now, in fact, be the confidentiality protecting mechanism used for the 2020 census. So 20 years of work. This work started, I guess, in 2002. You said, and the motivating scenario that you had at the time was the question of the Census Bureau and how it thinks about data and privacy, and here we are 20 years later with that technological invention creation being built in to the work that the census is doing. Professor Dwork is a member of the U.S. National Academy of Sciences, the U.S. National Academy of Engineering, and the American Philosophical Society, as well as being a fellow of the American Academy of Arts and Sciences. With all those accolades to her name, the other thing I want to say about her is just what an extraordinary intellect and human being she is, with a just incredibly voracious curiosity across all domains. It's no accident that she's got an affiliation in the law school and is a Radcliffe professor, as well as being appointed in computer science. And some of us at the Saffir Center have had the great pleasure of trying to wrestle with her this semester on the relationship between technological complexities, technical issues and questions in the development of algorithms, and the normative dimensions of those algorithms and their use in policy domains. It's been an extraordinary conversation. I've had just sort of taken great pleasure in the chance to get to know Cynthia and to probe these questions with her. So we will hear from Professor Dwork for about 45, 50 minutes, and then we'll have the chance to open up for Q&A. I also would like to thank Dean for being here with us tonight. Dean Elmendorf, thank you very much for joining us. We're delighted to be here in your Kennedy School space this evening. So with that, Cynthia.
I think I'm going to cry. That was just such a moving introduction. And working with Danielle this semester is why I'm here at Harvard. So, I've been working on, is the mic okay? No? Yeah. I've been working on these problems since about 2010. And I really feel like I'm just beginning. So let me tell you a little bit about what we've learned. The task that we set out to try to accomplish was to define what it means for algorithms to be fair and to build fair algorithms once we have this definition. And a really lightweight but motivating scenario, this work was done when I was at Microsoft Research, started when I was at Microsoft Research. So a motivating scenario might be online advertising. So you have a bunch of advertisers. You're running an advertising platform. You don't know your advertisers. You don't trust your advertisers. They can be absolutely arbitrary people. The decisions that are made about which ads to show to which people are made in a very small fraction of a second. And there's certainly no time to vet anything. And so how do you design something that will sort of be resilient to arbitrarily biased and nasty advertisers? So we have a population that's diverse. It has all kinds of diversity, ethnic, religious, geographic, medical, and so on and so forth. And the concern is what I'll call informally just differential unfairness, that we're treating members of these different groups differently in a way that we feel is unfair. So what's the first thing that everybody thinks of? The first thing everybody thinks of is, oh, if we're going to have an algorithm that's making a decision whether to show, let's say, a certain advertisement to a certain individual, let's hide from that algorithm the sensitive information about the person, which groups they belong to, for example. And that approach just doesn't work, and probably you all know why. Essentially, the sensitive attributes are embedded sort of holographically in all of our information. I mean, the fact that I'm a woman is embedded in many, many different things. The kinds of clothes I buy, perhaps the singing groups I belong to, the dance groups, and so on and so forth. So there's information that's coded in other, redundant ways, and that's redlining. And there's also a bird of a feather phenomena. So for example, a class project several years ago by Jernigan and Mistry at MIT showed something like this, that if you are male and if 5 or more of your Facebook friends self-identify as gay, then you're probably gay. So inferring things about an individual by the members of their social network and the things that the members of their social network choose to reveal about themselves. So there's another problem, though, with hiding sensitive information, which is that your classification algorithms will become less accurate. So here's a really simple, don't take it seriously example. Suppose you have a minority group, let's say S, a minority group in which the bright students are steered toward studying math. And in your majority group, T, the bright students are steered toward studying finance. And now, if you want to write a quick and dirty classifier to find bright students, it's fine to write a classifier that just looks for studying finance, because after all, it's going to be right on the majority. And that's what you want from an algorithm. It should be right most of the time. But not only is it unfair, but it's of reduced utility. If you're trying to find bright students, you need to know that students in the minority group who are studying math should be viewed as similar to students in the majority group who are studying finance. Or you should be culturally aware to what it is, how things are in the minority group in order to just make a more informed decision. So this also lets me introduce my names for the rest of the talk. I'm going to assume that the people in our population for now are neatly subdivided into the minority group that likes to flavor their food with sage and the majority group that prefers to use thyme. And the minority group is historically oppressed, but that's how we think about them, the sage eaters and the thyme eaters. Now, one thing that's really clear is that you have to collect the salient features for both groups, and they may not be exactly the same. So for example, if for these students we record simply the single bit of whether or not they study finance, we're not getting the differentiation capability that we want to have on the sage eaters, because the sage eaters, let's say none of them study finance and the smart ones study math. So it's not enough just to have one bit that says finance or no finance. You have to have at least 2 bits, one that says finance not and the other one that says math not. Okay? All right. Now, if I say that artificial intelligence, AI algorithms or machine learning algorithms train on historical data, is there anybody in the room who doesn't know what I'm talking about?
I'm going to put my hand up.
Yay, okay. Okay, fine, great. So, machine learning algorithms are trying to do a couple of different sorts of tasks. One kind of task is labeling something, cat or dog. So what you do is you give it a whole bunch of pictures of cats where you label them cat and dogs where you label them dogs, and you let them sort of learn what it is that these cat-like things, these things labeled cat have in common, and these things labeled dog have in common, and what's different between the things labeled cat and the things labeled dog. And that's how you train it. You give it all that information, and then it learns how, given a picture in the future of a cat or a dog, it can guess as to, pretty well which one it is. So you could have binary classifications. You could be classifying people as to whether they're well qualified for loans or not, or well qualified for school or not, or whether they're at high risk for developing a certain disease or not. You could also be training them to, you could have an algorithm that gets information about large populations and can learn things like what is the chance that somebody will develop a disease given the following medical information about them. So you might be learning a probability or you might be learning a label, and that's pretty much what happens. I think that's all you need to know about that. Now, one issue with training is that the algorithm is no smarter than the data that are given to it. And so if the data have historical biases, if they reflect bias, either because of the choice of features or even in the imposition of labels because you've been oppressing the sage eaters, and so you've been rating them as not qualified when they're qualified and things like that, then that bad behavior is going to be learned by the algorithm. So you can't just say, go forth and learn and reproduce. It doesn't work. And when you think about it that way, though, this whole demand of trying to develop fair algorithms is completely unreasonable. Where is the algorithm going to get the information from? You have to do something to help it along the way because history is not enough. So we will see something about that later on. Okay, so basically, there's no kind of built into the data source of ground truth, and we're going to have to do something about that. So, what's the general way that you go about trying to build something really, really new? Well, we have this fabulous paradigm from modern cryptography from the 80s. And it goes sort of like this. Well, it goes exactly like this. First of all, you have to define what it means for an algorithm to be fair. You have to define your goal. Sometimes that's more easily done by saying, what is it that someone who is trying to be not fair is trying to do? What is not fairness? And then our goal is to be not fair. So you can think about this when you think about, in terms of, let's say, what does it mean for an algorithm to encrypt messages well? Well, the adversary is trying to learn something about the encrypted message, about the plain text before the encryption. So you can define what it means for an algorithm to be a good encryption scheme by saying that the adversary can't learn any partial information about the message. So we want to do something similar here. So we want to say, well, here are these various things that an unfairness adversary will be trying to do. Those are things we want to prevent. Now, maybe our list will not be sufficiently inclusive. That is to say, we may have not thought of some things. And that's okay, because later when we think of them, we can change the definition and build a better algorithm that satisfies the new definition. In the meantime, we've prevented the things that were on our list in the first place. So it's not the end of the world if it's not completely comprehensive. But in any case, we want to define what it means for an algorithm to be fair. Then we want to construct algorithms that sort of mathematically, provably satisfy this fairness definition. And finally, nothing ever is done in a vacuum. There's not just one advertisement, one university student pair, one medical estimate that's going on. People are subjected to many, many judgments all the time. So we want some kind of an understanding of what happens when you compose or you build systems from individually fair parts. And so the third part of this paradigm is composition. Prove something about the fairness properties of the systems that are built from fair pieces. Okay, so today I'm going to focus on two things. Binary classification algorithms, so we're just trying to classify each person as positive or negative, say perhaps high risk for disease or low risk. And the other is what we'll call a probability estimation algorithm. So given an individual X, we're trying to produce the probability that, let's say, somebody will develop an illness or disease. And one way that I like to think about this is that each of us is holding a coin, and the coin has a certain bias. It's not a 50-50 coin. It's not a fair coin. And the coin actually is biased with exactly our probability of, let's say, developing the disease. And at some point in life, that coin gets flipped, and either we get it or we don't get it. So whenever I say coins, you should say, what is your probability space? I'm not going to answer that now, but you should think about that. Okay. So the boundary between sort of scoring and estimation and decision is not all that hard. So for example, This is an example of risk assessment scoring, which is used, I think, in Santa Clara County to classify arrested children and determine their eligibility for secure detention or release. And so it has fields for, let's say, what was the offense, what were the prior offenses, what were the mitigating factors, and points are assigned for the offense, the prior offenses. Points are then deducted for mitigating factors, and the whole thing gives some kind of a total risk score, which is the sum of these quantities, and then that can be translated into a decision by comparing the score to some threshold. So you started with the score, which was a number, and you turned it into a yes/no. And depending on the definition, fairness in scoring either will or will not result in fairness in the ensuing decisions. So just a little pointer here, when we think about these things, is the choice of features a potential source of bias? Are there things there that might be biased? Are there things that should be included that aren't being included? Whenever you see something, especially if somebody is claiming to you that it is interpretable, and notice I have that word in quotes, you should start looking. And they're saying, hey, look at our features. Look at them and see. Okay, so roughly speaking, definitions of fairness are partitioned into two groups, group fairness and what's called individual fairness. So we'll start with group fairness definitions. Group fairness properties are statistical requirements about how different groups are treated as a whole. So for example, as shown in this picture, statistical parity, also known as demographic parity, says that the demographics of the people that are assigned to a given classification are the same as the demographics of the general population. So if your population is, 25% sage eaters, then the yeses should be 25% sage eaters, and the nos should be 25% sage eaters. That's just demographic parity. So this is a nice, appealing notion. And in fact, if you don't have demographic parity, that might be a red flag that says you should look. Why? Why don't you have demographic parity? Investigate further. So it might be something that is sort of significant in the breach, but it turns out that it's quite flawed as a solution concept. In other words, it's not sufficient. And here's one example of a way in which it's a flawed concept. Intersectionality. So suppose in addition to having sage eaters and thyme eaters, we also have coffee drinkers and tea drinkers, and these sets intersect. So you might have an algorithm that has demographic parity with respect to the sage eaters and the thyme eaters, and it has at the same time demographic parity with respect to the coffee drinkers and the tea drinkers, but the sage eating coffee drinkers are treated terribly. So demographic parity for the individual groups didn't give us what we wanted when we had intersections. There are other problems with demographic parity as a solution concept, but I'm really interested in the intersectional case, so I gave this one. Okay. Now, going back to the situation where we're trying to estimate a probability for each person, we could ask for something which is called calibration within groups. So in this model, let's say people are given probabilities, assigned probabilities in some particular case of 0.1, 0.5, and 0.9. And what calibration within groups says is the following. For each group independently, and for each of these bins with their associated scores, these scores are correct on that group on average. So for example, if I look at all of the sage eaters who are mapped to the bin with probability score 0.1, then in fact the average of their true probabilities is 0.1. And if I look at all of the thyme eaters who are mapped to the bin with label 0.9, then in fact the true probabilities for all of those people on average is 0.9. It could be 1, it could be something much less, but on average they will be 0.9. So that means that this label, this value V, is correct in expectation for both of the groups, for the group S, the sage eaters, and for the time eaters. So that's appealing. It says that the score sort of means the same thing, whether this is a member of S or a member of T. But nothing forces even remotely comparable differentiation. So suppose in both of my populations, I have people whose true probabilities are just 0 or 1, and in fact, both populations are split exactly 50-50. And suppose my algorithm maps all of the sage eaters to the value of 0.5, which is in fact correct on average, right? You have a bunch of zeros and a bunch of ones, their average is 0.5. But on the time eaters, it's way better able to differentiate, and it maps essentially all of the, yes, I said zeros and ones, but I meant 0.1s and 0.9s. It maps all of the 0.1s to the bin called 0.1, and it maps all of the 0.9s to the bin labeled 0.9. And it's, it's calibrated, but these groups are not being treated equally at all. In one group, on the sage eaters, nobody bothered to differentiate and find those bright students. So, okay. Now, there are several other notions that are really, really desirable. So if you're making predictions that are binary, you might want that on the two groups you'll have equal false positive rates, and on the two groups you would have equal false negative rates, and some of you know the punchline here. And you might also want on the two groups to have the same positive predictive value, which says that among those who are labeled high risk, then in fact the same fraction of them are truly going to be offenders in both sage and in time. So the true ones is the same fraction of those labeled 1. And the problem with this is they're all desirable, but they cannot all coexist. You cannot simultaneously satisfy all of these 3 statistical requirements if the base rates are different in the two populations. And there are many variants of this result. This is just one example. So, pop quiz, is the problem solved by introducing a human into the process? No, because those are statistical conflicts. There's no way of assigning the labels that satisfies these 3 statistical notions simultaneously, whether it's done by hardware, wetware, or something in between. Another pop quiz, what if we put in a classification deity? Can that solve it? And the answer is not if you believe in free will. Okay, so the other approach to fairness is what we call individual fairness, which says very intuitively that people who are similar for the particular classification task should be treated similarly by the classifier for that task. So if you're advertising books, it's quite possible that for books that have to do with AI and ethics, Danielle and I would be very similar. And for books that have to do with Markov chains, we would be very different classification tasks. And of course, the problem with this approach is that you need the right notion of similarity or dissimilarity for the specific classification task, and where is it going to come from? So the statistical approaches, the group fairness definitions, are very easy to articulate, but they're not very meaningful, and they're in conflict with each other. This is, I mean, they are meaningful, but they have problems. You can hide a lot of sins inside these things. This notion is very meaningful and harder to hide sins inside of, but we don't know how to get our hands on the metric, on the notion of dissimilarity. Nonetheless, we're going to proceed because I'll say a little bit more about that. I do want to make a point. Suppose we're thinking about credit scores. And suppose credit scores are sort of smushed, what is it, between like 0 and 800 or something, uniformly, like they're very densely packed. So suppose you think, well, you have to draw the line somewhere. Like this credit score, above this you're in and below this you're out. Well, then you have 2 people one just above the line and one just below the line, and they're very similar because they're just above and just below, so they're really close to each other. And yet we have to treat them differently because one is yes and one is no. So how do we deal with this? We cheat. We randomize. So you don't get assigned a fixed you don't get assigned a fixed output. Rather, you get assigned a probability of getting a yes or a no, and then a coin is flipped to determine with that bias to determine what the outcome is going to be. So that way, two similar people should have similar probability distributions on outcomes. So this is nice, but there is question still. Not only where do we get the metric from, but what is it exactly that it ought to be expressing? So for example, suppose I have an individual X, and the way we think about this is that our individual has free choice or some internal randomness, and the universe or the environment that the individual interacts with also has randomness and unpredictability in it. And with those two sources of randomness, we can define, although we can't actually compute, the probability that X will succeed, let's say, at a nice news organization. X as a candidate employee, this is the probability, pi X, that X will succeed at nice news. So intuitively, if the difference between pi X and pi Y is small, then they should be assigned similar scores or have similar probabilities of getting the job. Okay? So that makes sense, it's what you want. But what if this is nasty news? And at nasty news, the sage eaters are traditionally discriminated against, and they're not likely to succeed. And you define success as staying in the job for, say, 3 years and having at least one promotion in those 3 years, and the members of S just don't succeed as well. So what is it that the metric ought to be capturing? And this is just a chance to point out that we kind of have two things in mind for some of the applications of fairness. One of them is kind of, what's our probability of success in the ideal world where everybody is treated well and is able to achieve her greatest potential? And we call those Q stars, probabilities. And then there's the real world, which is nasty, and people are oppressed and beaten down and so on and so forth. And they have a different probability of success, which is P star. And so the question is, which one should we be talking about and when? If we're trying to predict health outcomes, clearly the real world is the real world and you want to know. But if you're trying to figure out how you should treat people so that they can maximize their potential, you might want to be talking about Q star. How do you get your hands on it? I mean, it's not in the data, right? How do you know? Okay, so let's talk about algorithms for a bit. I've been talking about fairness, but fairness isn't the only question. We want the algorithm to actually be useful. So in the advertising scenario, for example, for each individual, there could be a value, or somehow we always talk about the lack of value or the loss that's incurred by showing this ad to this individual. But we can write it down. So the vendor, the person who's trying to do the advertising, may have some notions of, these are the people that I really would value sending to, and these are the people where I don't want you to send it because it's basically a loss of money for me. I'm not going to get anything from it. Or, I'm not a nice person and I don't want you sending that ad because I'm just nasty. And so I view this as high loss. Remember, we don't know, we don't trust our vendors at all. So, but the losses can exist, and the vendors can express them. And then we can assemble our information into a solution, which is actually expressed as a linear program, which basically is, intuitively, it just says minimize the utility loss subject to the fairness conditions, that similar people should have similar probability distributions on outcomes. So the loss function is viewed as a soft constraint. We make best effort. Whereas the fairness constraints, those are hard requirements. Fairness conditions are hard requirements. We insist on fairness, and we allow people to maximize revenue subject to those conditions. Okay, so there's a solution that is, given a bunch of people and these loss functions and the metric, you can figure out how you should assign adds to them or whatever your outcomes are. But what about people that you haven't seen yet? So, because it would be really nice if all this work that you spent figuring out how you should advertise to individual people, you could actually extend to new people who are coming, or to who, if you spend a lot of work deciding very fairly for a couple of years of students how you should be offering admission, then it would be nice to leverage that for future students, for future classes. So that process is called generalization. And the punchline here is that if you relax the requirements a little bit to what we call a probably approximately fair, as is done always in traditional machine learning, then you get generalizability. So now, what about building the metrics? So this is work, very recent work of my student, Cristina Elvento. Christina's suggestion is to combine insights from human interaction studies or understanding of what humans can do well with insights from machine learning to build a metric. And I'm just going to give you a little bit of the flavor of what she did. So first of all, there are certain kinds of questions that people find apparently easy to answer. So I'm showing you three candidates, A, B, and C, and an easy-ish question is, which of A and B is closer to C? So apparently humans have a pretty easy time with that. What they have a hard time with is quantify the distance between A and B. So this relative thing is pretty easy, but this quantify the distance is hard. Okay? Now, what we really want is for, if we have n people, we want all those n squared pairs of distances, the hard distances. So that sounds like n squared hard queries. And she shows, so her first observation is that you don't actually need to do something like that. So in a particular very simple scenario where you're trying to, we have kind of a one-dimensional measure and you're trying to just classify people yes or no, you can use easy queries to sort the points according to the distance from a worst or a best element. And once you've got them sorted, then you just use the hard queries to find the distance between adjacent points in the ordering. So instead of having n squared hard queries, you have n log n easy ones and n hard ones. And in fact, you can even get by with a constant number of hard queries. Now, of course, her work is much more general than this. It's not just this simple case where everything is nice and linearly ordered, but it gives you a little bit of the flavor of how you can be creative and use some human inputs in a not horrible, horrible, horrible way that lets you to start actually to build a metric. But you have to have somebody you trust for these human inputs. Okay. Now, I want to mention just a couple of additional approaches so that when you leave here and you start following the computer science literature, if you're not already doing that, you'll know what some of these things are about. One is what's called learning a fair representation. Now, the general idea here is the data are presented to us. Each individual is actually some point in a very high dimensional space where some of the dimensions have to do with attributes and histories and how old you are and what books you've read and all these sorts of things. And in the fair representation approach, you try to find a different representation for the data, typically much lower dimensional, that will stamp out the sensitive information. So that stuff that I said was holographically embedded, you're trying to stamp it out. And yet you want to retain sufficient information to permit standard training. Now, there are many reasons to be skeptical here, but this is also really exciting and intriguing. And I think it makes sense to continue to think about it. So I think it's a very fun direction. The other is a more standard theoretical computer science approach. There are algorithms, one for fairness. You've seen calibration. Remember calibration, we're assigning estimates of people's probabilities, and we require that for each of the output bins with a value V, the average true probability of the people assigned to bin B is the value that's associated with that bin. So the things are right on average. You can, so what these algorithms do is one of them will give you calibration simultaneously for large numbers of intersecting sets. And I will tell you a little bit later, if there's enough time, why I find that so interesting. Having said there are some things I don't like about calibration, there are still things I like a lot about this approach. And the fairness results, so the calibration stuff is sort of correct on average, and the fairness stuff is fair on average in some appropriate way of defining it. And the fairness results have to leverage some limited access to a fairness consultant, just as Vento's work had to make use of a human oracle. And there's another approach that's out there in the literature, which is causality-based. So these people think about data generation models and classifiers that are built on and that work with these data generation models. And the definition of fairness is intended, given the model, to rule out effects that are sort of caused by being a sage eater. So I think this is really fascinating, and some of the literature on this clearly is motivated by a spirit of wanting individual fairness, although the algorithms don't necessarily quite get there. But there is an issue that I don't understand how is going to be dealt with in the long term, which is there's a maxim in the statistics world, especially with respect to prediction models, is that all models are wrong and some models are useful. And if your definition of fairness is tied to your model, and if, as is often the case, given the data, you cannot tell which of several different models gave rise to those data, well, if the model is wrong, then I don't understand what the definition is giving you. It's not really telling you about the real world. So if it may putatively be fair, but it's not fair. And indeed, we've come up with examples where things are fair under the definition, and no human being looking at that would say it was the least bit reasonable. Okay. And then there's this. Okay. So I have just a couple minutes left, right? Composition. So there's a lot to say about composition, and I'm only going to say a little bit about it. Again, this is recent work with my student. So you might have the intuition that if all of the parts of your system are fair, then in fact the system as a whole should be fair. Whatever fairness means, this is a nice intuition. It would be great if it were true, but the reality is that it is complicated. And it's not automatically going to be the case, and I'll give you a really simple example from the advertising world. So I'm going to have two advertisers, and the two advertisers, do you know how ads are placed on your screen, banner ads? You know that there's actually an auction that goes on. That space, in a fraction of a second, is auctioned off to the highest bidder.
Our first lecture of the year was about that kind of auction, not in that context, but more generally, through the economies.
Great. So this happens. So we're going to have two advertisers, each one of which is completely fair on its own. One of them is advertising for tech jobs. So it's a company and it has a job and it's advertising for candidates. And the other one is advertising for a grocery delivery service. And they're battling it out for this banner ad at the top of your webpage when you go see the New York Times, let's say. So what happens? Well, one way to think about it is one of them bids a lot and the other one bids a little. And this is an auction. So the one who bids a lot, you can think of as simply going first. So my grocery service decides whether or not to bid on somebody. and it's bidding $1. Now, the tech company bids among those, basically, that are not claimed by the grocery store. Why? Because they're really bidding on the same people, but the grocery store wins because it's bidding more. So it's as if it's going first, and the dregs are left for the tech company. Okay, I didn't mean that, but now, when do people really, really, really get aggressive advertising from the grocery delivery service? When in real life do they get this? When they have a new child. And the web knows when you have a new child, okay? And then suddenly you're a target, and then, because if they get you then, when you really need the help, then you're probably going to be a customer for years and years and years. So you're extremely highly valued in real life. So that means that the new parents aren't seeing the tech jobs ads. Okay? Now, this actually, and the system isn't fair as a whole. And it's the competition that's making it unfair. Each of the two classifiers is perfectly fair in isolation, but because they're competing with each other, the one that's paying more is winning, and the results are unfair on the population. Notice that the tech company may be behaving very, very well and not knowing and not touching with a 10-foot pole your parental status. But because its competitors are legitimately looking at the parental status, it's hurting parents. Okay. Now, there is a non-naive solution. So naive solutions don't work. There is a non-naive solution. It can be expensive for the advertising platform, and it's an interesting question how much we can improve on the simple non-naive solution that we have. Okay. So that's a little bit about composition. And in the last couple of minutes, I'm going to talk briefly about group remedies, so fair affirmative action, or fair with our notion of fairness, affirmative action. So one way of trying to get some kind of affirmative action is through rankings. So many of you probably know this example that universities of Texas and California offer to the university position attendance to the top 10% of the students in each high school class. Okay. My understanding is that this works better at integrating the university in Texas because the schools are more segregated to start with. Another example, this is due to John Romer, stratify the students according to the education level of the mother. Within each stratum, rank the students according to the number of hours the student spends on homework per week, let's say. And then admit to the university the top K% from each stratum where K is chosen so that you get your university class of the size that you want. So both of these are sort of splitting people into disjoint sets and then ranking within the set. And another example from Professor Allen. It's a sort of a, degenerate form of this, because we're not really ranking, we're not getting the full power of ranking, but it's the solution she proposes is to stratify students according to their, SAT or some combination of SAT and grade point average. And basically, to discard, I shouldn't have used the word stratify, just discard all of the students below a certain fixed threshold, so below a 1200, let's say, on the SATs. And then among the students who are left, so I guess the stratification should have been according to zip code, you admit randomly so as to maximize geographic diversity, I meant to say. Okay? So, I'm sorry? At level of zip code, zip +4, yes. Good. So suppose you're doing one of these schemes. These schemes are similar. In Danielle's case, she just threw out everybody below a certain threshold, and then she's dealing with everybody else that's left. So here's a very, very simple version of what we can do in the, if we have a metric. So suppose for simplicity that we actually had the same number of sage eaters and time eaters, okay? Then what we do, we have distances for each sage eater. There's a distance to each of the time eaters. That's given by our metric. So what we do is we pair for each sage eater Si a single time eater Ti so that we minimize the sum of the distances of the pairs. And then to classify somebody a sage eater, we go over to their corresponding time eater and we see how we classify the time eater. And one byproduct of this is that we'll get demographic parity for free. That if we, give admission to the school to a third of the time eaters, we'll give it to a third of the sage eaters because of this one-on-one pairings. Now we'd really do something more complicated than that, but this is the gist of it. Now, in general, we know how to handle multiple disjoint groups or strata in Romer's case, or the zip plus 4s in Danielle's case. If we have a metric, we just handle them separately and in parallel without a metric from something called a fair ranking, which I will not get to today. And in Danielle's case, we would have in this, like the purple group, we'd have everybody in one zip code who is above threshold, and they're sort of all equally close to all of the time eaters, which is in a different zip code, all equally close to the rosemary eaters. Okay. But the intersectional case for this sort of approach remains open. We don't have a clue how to deal with that yet. It hasn't been a subject of a lot of work, but it's interesting. So, some final remarks. Skewed or rescued? When the data are sufficiently representative in all ways, then we're rescued. I mean, that we really can get a lot. We can really get rid of a lot of human bias and exhaustion and just kind of the vagaries of dealing with humans before and after lunch. When the data are insufficiently representative, things really are skewed. And you have to do something assertive to take care of that, to address that. So, can computer science help? Well, this looks like a complicated slide, but you actually already know the first 3 bullets. I'm reviewing what calibration is. Calibration, again, says within a group G, the bin labels V are correct in expectation. Multi-calibration simply says that for a collection C of possibly intersecting groups, the scores are calibrated for every single group in C simultaneously. So not just for disjoint groups, but for complicated intersecting groups, you still calibrate simultaneously. Why do I like this? Well, we can take our collection C to be all sets for which membership is easy to compute given the data. And it can be really easy to compute. And what I like about this is the following. Let's say you have a whole bunch of data about people and how they're being treated, and you're trying to understand, you're trying to know, is there a group that has been mistreated? Then what you want to do is you want to sort of think, okay, let me look at these various sets and see if they're really being treated fairly. But it's not always clear that, how do you figure out which sets you should look at? So going through some historical reading from the 1800s and the things that women said about themselves and their abilities and the way they put themselves down, at least in writing, maybe even these people did not think of checking to see were they being treated fairly because they didn't expect to be treated equally. So here, if we're just able to ensure this kind of, the right kinds of parity for everything that's sort of easy to describe, we should probably capture all of the traditionally underrepresented groups without putting the onus on the members of that group to fight for themselves. It'll happen automatically. And so I find this really, really intriguing. That's why I like that stuff so much. So yes, I think computer science can help. I think in directions like that. Can computer science manage without wise inputs? Not for now, no, I don't think so. Can the input process scale? I don't know. I think it's a really interesting question. You know, to have one wise woman giving all of these estimates of who's similar to whom, it's like a lot of work. So it's too much. Defining fairness is a political process. You know, Danielle kindly mentioned the work on privacy. Privacy was a breeze compared to this, because while people didn't all agree on privacy, it was on what it meant, it was possible to come up with a definition that everybody was able to at least find compelling. Here, I don't believe that's the case, and I think that in different contexts, it's going to be radically different anyway. So who chooses the definition for the context and how? We like to use randomness. Is randomness okay? So I've got 10 people that need to be imprisoned and 5 prison cells. Do I choose randomly? Is that okay? Is that fair? You know, my colleagues in the law school, you know, they go like this. All right. Standards of accuracy are context dependent. So in some cases, you really, really, really want to be as accurate as possible. And in other cases, it's not that big a deal to get it wrong. So, you know, okay. And just one example where it is high stakes, my last comment. There was a mention of recidivism prediction earlier. So there was a report to the president from the President's Council of Advisors on Science and Technology about forensic science in the criminal courts. And they were talking about things like, what are the kinds of standards you should have for DNA matching? That was pretty easy, but hair samples, fingerprints, and so on and so forth. You know, methods of looking at features of individuals and deciding whether there's a match or ruling out a match. So those are both important in the context of law. And they sort of lay out what they call foundational validity and validity as practice. So foundational validity was things like that the method should have reproducible and consistent procedure for identifying features within the evidence samples in the first place, comparing the features, determining whether there is a match, determining whether there's not a match, empirical measurements of false positive rates or false negative rates, or both actually. So that's sort of foundational validity. That's what you want if you're going to be using something in a high stakes decision. I don't think I've seen any real discussion of holding machine learning algorithms to this standard, even when they're being used in this kind of a situation. So, and validity as practice basically says, is the person who actually carried out the test capable of carrying it out correctly? And we could apply that also in the machine learning setting. So that's what I'd like to end with. It's just like, there are real practical things that we can do right away to try to use these things more wisely. So thank you very much.